automatically know, like, yeah, this is definitely water. Yeah. And then the stress is gone versus if you're like, am I right? I'd be right. I feel like I was right.
Well, thank you for that. That's taking strategy.
You're welcome. They can make
Oh, you know where I'll be like, no. And then you make a list. These are the things I would have no idea what's going on. And it's over there. You can make a list of more too.
I need him to show up.
I like the right side.
You're still in the front row though. You just like walk out and walk in. You know what? You seem like a color. I just never.
Okay, everyone. Last session we talked about chemical reactions, and without looking at the board, do you remember what was a chemical reaction? Can anyone tell me? No one? Yes? So color change can be an evidence of a chemical reaction, yes. But what is, if I ask you in the test, what is a chemical reaction? What would you say? So can you give, yes? Exactly. So we have like, one or two substances, they react and then they create new substances. And we had different types of reactions, and then I gave you some examples of those. Can anyone tell me, with or without looking at the board, what are some types of reactions? Yes, precipitation. What else?
Combustion.
Yes. What else? Gas evolution reactions, yes. What else? Exactly, oxidation reduction reaction. And can anyone give me an example of a precipitation reaction?
Hydrogen and oxygen from water.
So that is not a specifically precipitation. So what is the definition of precipitation reaction?
Reactions that form solid substances in water.
So yes, so what will be generated in a precipitation reaction in water?
Solid substance.
Exactly. So we gave examples of the laundry, previous session, that if we have a hard water and then if we don't use laundry detergent, if we use soap, specific elements of soap reacts with like magnesium or calcium ions, and it forms like some slimy material, basically some sort of solid. So that is a example of precipitation reaction. And I just want to quickly as I can kind of like review this for you. And everything that I talk about in the class, all these definitions, I'm going to ask you in the test. So study them well. I give you what is a chemical reaction. I give you 4 definitions, just one of them is correct. Or I say what is not correct about a chemical reaction, and I give you 4, answers. One of them, or one of them is not correct, depending on how I design the problem. So everything that I'm telling you, I'm going to ask you. So I encourage you to remember them well. So precipitation reaction is a reaction that a solid or precipitate forms upon mixing 2 aqueous solutions. And last session, we talked about aqueous solutions, that basically substances, when they dissolve in water, we call them aqueous solutions. And then I'm going to talk about them more as I go. But you remember that you have solid in precipitation reaction. What was gas evolution reaction? Can anyone give me an example of gas evolution reaction? Anyone? So what was the first example that I gave you last session? What's that? So that was combustion, but something, what is it? So we had like 2 things that we combined, and then we saw bubbles of carbon dioxide. I showed you a video. Exactly. So we have baking soda and vinegar. If we mix them, we see like bubbles. So that is gas evolution reaction. So that is a gas forms upon mixing 2 aqueous. Basically, it means that these are dissolved in water. Aqueous means in water solutions. And then oxidation reduction reaction. Can any of you give me an example of oxidation reaction? Exactly. And then the definition is electrons transfer from one substance to another. So what is combustion reaction? Can anyone give me an example of combustion? What's that? Exactly, like burning of the fuel or gas in the vehicle or like of your car. And then the definition is that substance reacts with oxygen and it generates lots of heat. So substance reacts with oxygen emitting heat and forming an oxygen containing compound, and in many cases water. So basically your fuel, your material, anything that you're burning reacts with oxygen, and then it generates lots of heat and an oxygen containing species, and in most cases water. So these are kind of the things that we talked about last session. And also I told you about I'm just going to write the title, and I encourage you go refer to your notes and also to the book, because I don't have time to just review everything from last session, but we said that the best evidence of a chemical reaction is the analysis of the reactants and analysis of the equation, the chemical equation, and then the reaction to make sure that the reaction has occurred. Because there are lots of reactions that we don't see an evidence or like something that shows us with our eyes that the reaction occurred. So the chemical analysis of the chemical reaction is the best evidence of a chemical reaction, but nonetheless, as your friend mentioned, there are like some reactions that, you see color change. So, I gave you an example that if you, have like these baby spoons and then you heat them, put them in microwave, or like, with the pass of time, you see color change. Even like when you wash them with hot water, although they, won't be damaged, but as time passes, you see color change, or like in your clothes, if you put them in front of the sun. So one was color change. What was other evidences of chemical reactions? So like, burning, like combustion. How do you know that a chemical reaction occurred? Anyone? Yes, exactly. So what are some other examples? So we talked about precipitation reaction. What do we see that we know that, okay, a chemical reaction occurred? Anyone? Exactly. Or like in the gas evolution reaction. So when we have like baking soda and vinegar, what do we see that we know a chemical reaction occurred?
Changing of the material to just like the base substance like carbon.
Yes, so it's not exactly carbon itself, but it's a gas. What is it?
Like in combustion, it leaves behind carbon, so it leaves behind the product. Or not a product, but it can leave behind a substance.
Yes, but specifically in this example, with like baking soda and vinegar, what do we see?
Oh, a big sugar. Sorry, I was talking about combustion.
Yeah, that's one. But in this example, what do you see that
Carbon monoxide or dioxide.
Exactly. So you see like bubbles of gas, you see gas. So like formation of gas, formation of solid, color change, and formation of heat and formation of light. Also, if you see that a building is burning, you also if you're close, you see the heat, but if you're far, you see the light, right? And the other one was like heat absorption, like this ice pack example, that if you separate the two parts of the ice pack, you see like you feel the cold because they absorb heat. So heat absorption is the other one. So I'm not going to write these, but I just told them. So we talked about chemical equation. Now, can anyone tell me what is a chemical equation? Or why do we write a chemical equation? Exactly. So you want to see your products. You also want to see your reactants, and you want to see the states of the substances in your reaction, right? And you also want to know the number of atoms or molecules in a chemical reaction. So in other words, if you want to visualize a chemical reaction or have an understanding of a chemical reaction, you should write a chemical equation. In other words, chemical equation is a representative of a chemical reaction. So, for instance, let me just write the definition. Chemical equations represent chemical reactions. So let me give you an example. For instance, if you consider, some stoves, they use methane, and you can see the flame, right? You see the blue flame. So that is kind of like a combustion reaction because methane is reacting with oxygen and produces carbon dioxide and water. So we write this reaction as this. And when we finish this chapter and then learn exactly how to write chemical equations, I'm going to ask you basically the same thing that I said. I will ask you to write me the chemical equation. So be prepared for that and then pay attention. So in this chemical equation, the substances on the left of the arrow, the substances before the reaction occurs, we call them reactants. And then on the right-hand side, you have the things that are produced after the reaction. So basically, these reactants, CH4 and O2, something happens between them. They go through some, changes, and then they form other substances. We call those other substances products. Any questions so far about what is chemical reaction, what is chemical equation, evidence of chemical reaction? Is everything good so far? Any questions? Okay. And as you remember, in last session, I told you that we write the state of each of these compounds because we want to know as much as information about the chemical reaction by just looking at the chemical equation. And I told you that, the methane is gas plus oxygen, which is gas, gives us CO2, carbon dioxide, plus water. And I also gave you a list of different states, like gas is G, just you use the first letter, Liquid is L, solid is S, and aqueous is AQ, which is like the, means, that specific substance is dissolved in water. So I just write this here. And I'm going to talk in more detail in next section that I'm going to talk about today. But just for now, know that aqueous means dissolved in water. And when a substance dissolves in water, the mixture is called a solution. So if I ask you what is a solution, it's simple. When a substance dissolves in water, we call that mixture a solution. For instance, a solution of salt in water or sugar in water. If that specific substance dissolves in water, we call that a solution. Any question about aqueous and solution? Are we good so far? Are you following me? So one thing that is really important, in chapter 3, you learned law of conservation of mass. Can anyone tell me what law was? Does any of you? Yes. Exactly. So here, I'm going to write it because it's really important in what I'm saying after this. So matter is neither created nor destroyed in a chemical reaction. So what does that mean? So imagine, so I'm telling you because the next concept that I'm going to teach you, which is balancing chemical equation. So the same equation that I wrote, methane plus oxygen gives carbon dioxide plus water. So based on law of conservation of mass, matter, is not created or destroyed. So here on the left hand side, if you have like one carbon atom, on right hand side you also should have one carbon atom, because they just, they don't disappear, they don't be generated. If you have like one carbon atom on the left, you should have one carbon atom on the right. If you have like, if you don't have sodium on the left, you shouldn't have sodium on the right, So basically, if you have carbon, hydrogen, oxygen on the left, on the right hand side you should have carbon, oxygen, hydrogen. And also the number of atoms, total atoms on the left should equal total of number of atoms on the right. Otherwise, the law of conservation of mass is not being, met, it's not valid, and we don't want that, it's not happening. So we always have that. So is it clear what I'm saying? Okay. So for that matter, here, and this is something that I gave you in the quiz too, and I'm going to ask you in the exam too. So for instance, in CH4, I'm just writing this one by one, so you remember, refresh your mind. If you have like one molecule of methane, CH4, can you tell me how many carbon atoms is in one molecule of CH4? Exactly. So we have one carbon. How many hydrogen? Exactly. So what about oxygen? How many oxygen atoms do I have? Yes, I have 2 oxygen. And as you remember, there are like some elements that they exist as diatomic molecules, like oxygen, O2. We had some others too. So just go back to chapter 5. Remember which atoms were like just like, which elements were just like, single, which one were like, forming diatomic molecules, which one were forming ionic compounds, and so on and so forth. So here, what about the products? I have CO2. How many carbon atoms CO2 has? Yes. What about oxygen? Yes. And now water. How many hydrogen atoms water has? How many oxygen? Okay, so individually how to count atoms in molecules. But in chemical reactions, when we want to balance the equation, which means we want to have the same number of atoms on the left side of the equation that you have on the right side of the equation, so that the law of conservation of mass will be preserved. So to do that, we just basically add the number of carbons in our compounds on the left side. We do the same thing for the right side. In other words, if I'm going to write the equation again, so it won't be cluttered with the other things that I wrote. Okay, so individually in CH4 how to determine how many carbon atoms you have, and then in CO2 how many carbon atoms you have, in oxygen, O2 how many carbon atoms you have, and how many in water. So can anyone tell me, on the left hand side, which I call reactants, how many carbon atoms do I have? Yes, have like 1 carbon. How many hydrogen do I have on the left side? What about oxygen? Yes. What about the products, which are like things that are being generated on the right side of the equation. How many carbons do I have? How many oxygen? Yes, 2 plus 1, right? I have like 2 here, and then 1 here would be 3 overall. How many hydrogen do I have? How many? Yes. So basically, law of conservation of mass tells me that, first of all, if I have CHO on the left side, I should have like CHO on the right side. And it tells me if I have 1, 4, 2 on the left side, I should have similar on the right. But as we see, we don't have exactly the same number of atoms. And it doesn't necessarily means that I should have like 1, 4, 2 necessarily on the left, or 1, 2, 3 on the right. But these numbers, should be equal, but they can be different too. So for instance, whatever I have on the left doesn't necessarily mean that it should be these numbers. So, I have like I add coefficients. I guess I use another color. I, add coefficients here. I just call them like whatever you want to call them. I should change these coefficients to kind of make these numbers equal, and I'm allowed to change these numbers. But I'm not allowed to change these subscripts. Can anyone tell me why I'm not allowed to do that, but I'm allowed to change coefficients? Yes? Exactly. So if I change, this CH4, to like only, CH 5. If I change that, I would be having like, pentane, not methane. I would be having different compounds. Or if I change, H2O to like HO, or like if I change like CO2 to CO, it would be carbon monoxide. It won't be carbon dioxide anymore. So I'm not allowed to change the subscripts. But I'm allowed to change the coefficients. Think of a chemical reaction as like baking a cake. So when you want to bake a cake, you have like flour, eggs, sugar, baking powder. What else do you have? Has anyone baked a cake before? So you have like some, ingredients. You can look at them as your reactants, right? And then when I bake a cake, when I have it ready, I put it in the stove and then have it like nice and warm. And then when I'm eating it, do I feel it is salty? I added sugar, right? So I don't feel, I don't taste salt. Why? Because, if sugar is glucose, it is, and salt is sodium chloride. So if, I put a cake, I put sugar in a cake and then I taste it is salty, it's kind of like magic, It won't happen. Why? Because I have like carbon, hydrogen, oxygen here, and then in salt I have sodium and chlorine. So as, the law of conservation of mass told us, matter is not generated, or like destroyed. So these atoms won't be destroyed and then generate something else, like in this case, sodium chloride. So this is wrong. So just remember that in your chemical equation, whatever elements you have on the left, you should have on the right. You don't have something that you don't have. And as your friend mentioned, we cannot change the subscripts because we don't want to change the molecules, We don't want to change the substances or the compounds. What we can change to balance the equation is the coefficients. Any questions about anything that I said so far? Everything's clear? Okay. So now it's the fun part. Actually, we want to balance this equation. And then in a balanced equation, the number of atoms in the left side of the equation, basically your reactants, equals the number of atoms in the right side of the equation, your products. I'm going to write this too because I'm going to ask you. Balanced equation. The numbers of each type of atom on both sides of the equation are equal. So now I'm actually to do it. Then you know that this is gas, this is gas, this is gas, this is gas. And your book has a really nice, example 7.2 that guides you how to balance a chemical equation. And when I learned this, we were told that balance this equation. And then we were struggling with the numbers, changing the numbers. It wouldn't make sense. And gives us lots of headache. And then we learned ourselves how to balance the equation. So it would be fun, or it would be a better learning experience if you kind of would try to balance the equation yourself and then would know how to do it. But I don't have time to do that, unfortunately. So I'm just going to tell you how to do it. So when you want to balance a chemical equation, sometimes you have elements or molecules, that they are diatomic or monoatomic. What I mean is that if you see just an element by itself, for instance, just like sodium, or only chlorine, or oxygen by itself, although it's diatomic, but it's just one type of atom by itself. It's not in a compound. It's not like CO2. It's not like H2O. It's just one type of element. Any questions? Any questions? Okay, so if you have an element by itself, you do, balance that type of element the last. So now, so we start with carbon. So how many carbons do I have on the left side of the equation? You just said that to me some minutes ago. How many do I have on right side? So carbon is good as of right now. So I, put a check mark here. And you don't have to do that. I'll just do it for myself to know that, okay, carbon is good. And I told you to do oxygen the last. So what is remaining is hydrogen. How many hydrogen do I have on left side? How many hydrogen do I have on the left side? 4. How many hydrogen do I have on right side? And then I told you we add coefficients to make this right. So yes, we added 2 coefficients of 2 before water. So now tell me, how many hydrogen do I have on left side? How many do I have on right side? So hydrogen is good too. Now only oxygen is remaining. And so I told you that we, do this the last. So I don't count this. I go to the right side. How many oxygen overall do I have on the right side? How many? 4. So how would I have 4 oxygen on the left side? Yes, adding a coefficient of 2. So now tell me, how many oxygen do I have on left? How many do I have on right? So now your equation is balanced. So how did we do it? We considered, we decided to do the element that is by itself the last, and then we kind of like started with carbon in this example and balanced that one, and then we went to the next one, hydrogen, and then we did oxygen the last. And as you go, when you are done, you should count the number of atoms to make sure that the number of atoms of each element on both sides are equal. Any question about this? Is it clear how we did this? Okay. So now let's look at SiO2 solid plus carbon solid gives SiC solid plus CO gas. So with which element do you start your balancing or your analysis? Which one? Yes. So how many silicon do I have on left? Okay, how many do I have on right? So that is good. What is the next one? Yes. And can anyone tell me why the next one is oxygen but not carbon? Exactly, carbon is by itself, so we do that the last. So how many oxygen do I have on left? How many do I have on right? So how would I balance that? Yes. So if I put 2 here, now tell me, how many oxygen on left? How many on right? 2, 2. Is it clear? So you multiply subscript by the coefficient. So now, how many carbon do I have on right? How many? Yes, 2 plus 1 is 3. So I put 3 here, so it would be 3, and this would be 3. So now your equation is balanced. So is it clear how we do this? And then your book gives some more examples too. I encourage you to study them. But for the sake of the time, I'm going to go to the next section, which is aqueous solutions and solubility. Basically, compounds dissolved in water. And I, kind of told you about aqueous solutions before, but I'm going to write them here too, because as I said, I'm going to ask you in the exam. So an aqueous solution is a homogeneous mixture of a substance with water. So if you add a substance in water and it forms a homogeneous mixture, that is a solution. For instance, when you add salt in water and then you just dissolve it, stir it, you don't see the salts anymore. It's a homogeneous mixture. So that is a solution. But if you put sand in water and dissolve it just with the spoon, you still see the sand. So that is not a solution. It should be a homogeneous mixture. And then you have another definition. Electrolytes. So there are, just imagine the example of salt that I gave you. When we have sodium chloride, and then when we stir, we have like some salt, we put it in water, stir it, you don't see sodium chloride itself. In fact, you won't be having sodium chloride in water anymore. These ions that form sodium chloride, they dissociate and they form Na plus and Cl minus in water. So if you could, see the particles of salt after being dissolved in water, you wouldn't see NaCl anymore. You would see Na plus and Cl minus. So these types of solutions, basically these types of compounds that dissociate in water, and they can basically generate electricity. So basically when they can so if you have you can use them as electrolytes, and they can basically conduct electricity. That is the term I was looking for. So right now, let me just write you the definition. Substances such as NaCl that completely dissociate into ions in solution are called strong electrolytes, and the resultant solutions are called strong electrolyte solutions. So any question about electrolytes? And then we have some more definitions too. So do you remember, based on the explanations that I gave this session, what is solubility? Or when do we call a substance soluble in water? Exactly. So, solubility. A compound is soluble in a particular liquid if it dissolves in that liquid. And then insoluble is the opposite. A compound is insoluble if it does not dissolve in the liquid. And then I'm going to write what I told you earlier here too. So NaCl, for instance, is present as So as I told you, when we dissolve NaCl in water, we don't see NaCl anymore. We have like Na, plus and Cl plus. So present as independent sodium and chloride ions in solution because sodium chloride solutions conduct electricity, which requires the presence of freely moving charged particles. So basically in electrolytes, if you have electrolyte, when you dissolve it in water, you will be having electrolyte solution. It means that, as I mentioned, for instance, in salt, the ions or like the constituent ions, they dissociate, you will be having Na plus, Cl minus. And because you have like freely moving charged particles, they can conduct electricity. Any questions about this? So you will be having a table, basically table 7.2, that it might seem a little scary to you. So in this table, or maybe the light was better, was it? Maybe? Okay, so in this table, you are given different, the compounds that they contain, ions that are like freely, that are mostly soluble. So it's basically your solubility rules. So there is no, mathematical formula or a way that you can, we did some calculations last chapter, for like moles, and then everything was like conversion factors. You don't have something like that when it comes to solubility. So for instance, NaCl solves in water well, but AgCl, it doesn't. So in order to know which, ionic compounds or like, which compounds in general, dissolve in water, which of them they don't, you have a table that you should memorize to know if I give you a compound, would that dissolve in water or not. And then just going through this table, and then equivalent to that is figure 7.7, which is basically the same as this table. I'm just going to walk you through the table. So the compounds containing the following ions are mostly soluble. So if you have, lithium, sodium, potassium, ammonium, they don't have any exception. If you see an ionic compound, if you see in general a compound that has any of these ions in it, that is soluble. And it doesn't have any exceptions. The same thing for like NO3 minus and C2H3O2 minus. And as you remember, I told you in previous sessions and then in office hours several times that I'm going to give you table 5.3 in the exam, but you should have familiarity. So when you see this NO3 minus, you should know that is, at this point, for this chapter that I'm teaching, you should know that is a nitrate. But I'm going to give you this table in the exam. And something that now that we are in the subject, this table, I give you lots of questions. I already gave lots of questions in the quiz, and I'm going to give you in the exam. This one you should know by heart. The metals whose charge is invariant, is like alkali, alkaline earth, aluminum, zinc, silver. And then this table over here is really important too. You should know that. Some common anions. So anyway, so nitrate and acetate, if you have these two polyatomic ions, without any exceptions, they dissolve in water. And then for others, for like Cl minus, Br minus, I minus, for those, many of them are soluble, and these are their exceptions. And I encourage you to read this chapter, this table, and also chapter 2, line by line, because this is the way that you can know which compounds are soluble in water and which ones are not. And then for these ones, these are compounds containing the following ions are mostly insoluble. So for instance, OH minus, S2 minus, and then CO3 minus, PO4, 3 minus. And these are their exceptions. And these ones you should know. Basically, this table is really important and you should know. And something that I wanted to emphasize at the beginning of the class for your exam, I'm giving you almost half of the exam or more conceptual problems because I want to increase your grade. And I thought that is the best way. You have 40 problems, 40 questions for your exam. Most of half of them are conceptual. So if you don't know the concepts or definitions, I don't know what happens. Your grade would be really low. So study them well, and I'm going to also post a study guide for chapter 5 and 6 for the definitions specifically, because the naming ionic compounds and the molar, chapter 6, the problems, I posted online, in like Zoom sessions, and I talked several times about them, so I hope you know them well. But for the sake of conceptual, problems and also definitions, I'm going to post a study guide that I highly encourage you to study, because if you don't, you miss like half or third of the exam. So just you go through the book, study the definitions and kind of like these extra definitions or like points that are listed. Yes? What's that? So I try to post it, today, so you can study during the weekend. Any questions about anything, whether the exam, quiz, things that we talked about?